Today, we're going to take a quick look at how I program microcontrollers. Welcome, I'm Dr. Plague. This video is designed to prepare you for some future videos that I plan on creating that will use microcontrollers. What I'll be covering today is which microcontrollers I'll be using and why, the programming tool that I use, how I make breadboardable programming headers, and we'll take a quick look at my preferred IDE along with a quick example showing how to program some code into a microcontroller. This video is geared towards those who want to follow along in my future videos and make some of the projects that I'll be showing. But anyone who wants to see how I program microcontrollers may find this video useful. And to be clear, this video is only going to show you how I program these microcontrollers. There may be other tools, IDEs, or methods available. Let's get started. As you can probably guess from the title of this video, the microcontrollers that I'll be using are the 8-bit AVR series. These were originally manufactured by Atmel, but after a buyout in 2016, they are now made by Microchip. Other popular 8-bit microcontrollers include the PIC family of microcontrollers from Microchip. Oddly enough, I started out with PICs, but one of the reasons I stick to AVRs is due to an employer that I used to work for. They used Atmels almost exclusively. They had their own manufacturing facility with a stockroom of parts to build boards. They wanted to keep their selection of processors to a minimum to help with pricing so they could purchase in quantity and have fewer selections to manage in their stockroom. So I became more familiar with AVRs and other Atmel ARM processors. So it is just a preference for me to use AVRs. You could choose other microcontrollers if you are comfortable with porting code to them. There may be some low-level code that I'll be creating that may be difficult to port to another processor, so you might want to consider using the processors that I use if you want to build any of my projects. One of my favorite go-to microcontrollers is the ATmega 1284. It has 32 I/O pins, 128 kilobytes of flash memory, 16 kilobytes of RAM, and operates at speeds up to 20 MHz. There are other variations with less memory, such as the Mega 164, Mega 324, and Mega 644. This may be overkill for many projects, and in some cases I'll choose other chips, such as the ATmega 328 or even the ATmega 48. For breadboarding, I choose through-hole versions in DIP packages, but when I design circuit boards, then I use surface mount versions. These are great microcontrollers to get started with. But one thing you will need is a tool to program them with. What I use are these AT-Atmel ICE programmers, or in-circuit emulators. And it is always good to have more than one, in case you fry one. Then you don't have to wait for another to arrive. There are different versions that you can purchase, starting at around $80 for just the PCB, and up to about $180 for the full kit with an enclosure like this one. These used to cost a lot less when I got them, so it's understandable if you don't want to purchase more than one. You know, when I first got started, I used free tools to program these processors, and I made this here programming connector that connected to a parallel printer port on a PC. Those were the days. But to do any serious programming, I would recommend to buy the proper tool, but I'm sure you could search the web and still find the info on how to program these for free. Now, you're going to need a programming header to use the AT-Atmel ICE programmer. Well, you don't absolutely need one, but it will make things a lot easier. There's a cable connected to the AT-Atmel ICE that has a 6-pin connector at the end. We need to build a programming header that we can place on a breadboard that this can plug into. What I use are these plated through-hole prototyping boards. You can pick these up at DigiKey and I'm sure other places as well. I'll put some info about these boards in the video description. Any type of plated through-hole boards like these will work as long as you can cut them down to size. I like to use this mini cutoff saw, which I bought from Harbor Freight. The last time I saw, they sell them for around $40 US. You could always get by with a cheap hacksaw like this, or maybe just score it with a utility knife and break it apart. I do have a bandsaw and a scroll saw, but I wouldn't recommend them for cutting such small items. Also, the scroll saw blade moves both up and down and cuts on the downstroke, but it could grab the board on the upstroke, and thus is too dangerous for my taste. I can get 4 programming headers per board by cutting them through these holes. Remember to always use a face mask when sawing to avoid breathing in the dust. Next, I take some thin 30-gauge wire and strip off about 3 inches of it. Then I weave it into the holes on this small board like this. I make sure that I start from one of the corners like you see here. Now I just add some solder to these 6 holes. Then I can cut away the wires at these points. And here. Now I take a 2-row header and cut off a length of 3 pins like this, and place it into the middle of the board, making sure that the pins insert into the holes in the same direction that the wires are bending into the holes. This is why I need such thin wire, to fit both the header pins and wire into the holes. Then solder the header in place. Next, cut 2 pieces from a single row header that are both 3 pins in length. And we press them into the opposite side of the board like this, and then solder them into place. I like to plug them into a breadboard so that they get soldered in straight. Now our programming header is ready to use, and you just need to wire up the header to your microcontroller. The thin wire is used to connect the inner header to the outer headers. You may be able to find boards that have traces connecting the holes so that you don't need to add the wire, but I would make sure that the holes are plated for extra strength, since we may be disconnecting and reconnecting to these headers quite often. Also, since we are soldering headers to both sides of the board, we need the traces on both sides connected. If you know of an easier way to make a programming header, then please leave a comment. My ways aren't necessarily the best, so I'm always open to suggestions. For the IDE, or Integrated Development Environment, I like to use Atmel Studio version 6.2. I believe MPLAB X also supports AVR processors, but I still use Atmel Studio 6.2. It's free. Just search the web for Atmel Studio 6.2. There is a version 7 available, and it is now called Microchip Studio, and I haven't tried it since they changed the name from Atmel to Microchip. But what I can say is that I do have Atmel Studio 7 installed, and the built-in simulator does not work correctly. I don't remember what the problem was, and I don't know if they ever fixed it, but I did open a ticket with Atmel's technical support and was told that the simulator does not work in version 7, and that if I wanted to use the simulator, I had to use version 6. I have not found any need to use version 7, so I still use version 6.2. You can certainly try version 7, but if you can't get the simulator working, then I would recommend installing 6.2. You can have both versions installed on the same computer and switch back and forth, and I do have both installed on all my computers. Now, let's take a quick look at Atmel Studio, and I'll show you how to start a new project. Just go to File, New, and Project. Now, you can choose between 3 installed templates: C/C++, Assembler, or Atmel Studio Solution. Normally, I would choose a GCC C executable project or a GCC C++ executable project. But sometimes I'll want to write some code in assembly language, so I would choose Assembler. Then choose a location and give the project a name. Now click OK. Now you're given a choice of devices or microcontrollers. Remember I said my go-to microcontroller was the ATmega 1284? Well, let's find it. There it is. Click on the ATmega 1284 and click OK. Now you're ready to start writing some code. But first, let's breadboard a very simple circuit. And this is the schematic. Now, let's connect the AT-Atmel ICE programmer to the programming header right here. Make sure the cable is plugged into the AVR port of the programmer and not the port labeled SAM, which would be used for the ARM Cortex processors. Then you can enter this simple code to set up a timer to blink the LED, or just make up some code on your own. Technically, we don't need this jump to reset, since I'm not using any interrupt vectors, but I like leaving it as a placeholder. I'll set the pin connected to the LED as an output. And then I'll set up timer counter 0 to toggle that pin. Then we'll just go into an infinite loop. Next, build the solution by clicking on this icon. You can also access it under the Build menu, or just press F7. You want to make sure that the build succeeded with no errors. And after you've written some code and successfully built it, you can click on this device programming icon with the lightning bolt to load the code into the microcontroller. You can also access it under the Tools menu, or by pressing Ctrl-Shift-P. Be sure you apply power to your circuit before programming the microcontroller. Make sure that the tool is set to Atmel ICE, and that the interface is set to ISP, then click Apply. We want the ISP clock to be less than 1/4 of the device frequency, which in our case is 1 MHz by default. So 223 kHz is fine. Then we can read the device signature and verify the voltage. We can change any of the fuses if needed, but this default configuration looks fine. Then, to program the microcontroller, click on Memories, and finally, click on Program. Everything programmed fine, and we can see that the LED now blinks. Now, let's take a quick look at the built-in simulator. This can help you write some code and check out the functionality without needing an actual microcontroller or programmer to execute the code. The first thing I want to do is to alter the code a bit so that the signal controlling the LED toggles every clock cycle, so we can see the changes as we single step through the code. Now I'm going to change the tool to the simulator. I'll click here to add a breakpoint. This will cause the code to pause here when we run it. And to run the code, we can click the Start Debugging arrow up here. Notice that it took 2 clock cycles to get to that point since we had to jump to the breakpoint. We can step into or step over with these icons up here. This will allow us to single step. So let's single step, and you can see that the cycle counter changed to 3, meaning that the LDI instruction only took 1 clock cycle to execute. I'll change to the I/O view, and we'll look at the port B registers. And if we single step again, you can see that bit 3 of the data direction register was set after the out instruction was executed. Now I'll single step until we get to the loop. Then the next single step sets bit 3 of the pin B register, and this would turn on the LED in actual hardware. Now that bit continues to toggle, which would blink the LED. And that's how easy it is to simulate some code. Just click here to stop the simulation. You can also create a C or C++ project and write your code in one of those languages. Here is the same LED blinker written in C. And that's how easy it can be to program an AVR microcontroller. You can refer to the microcontroller's datasheet to learn more about programming it. Well, that's all that I have for today. Be sure to check back for future videos where I create some microcontroller projects. If you liked this video or it helped you out, then please peck at that like button. And don't forget to subscribe if you haven't already done so. That way you won't miss any of my future videos. Thanks for watching, and I'll see you next time, right here on Dr. Plague.